Hello everyone, I'm Asım Emre Taşkıran, a mechanical engineering student at Bilkent University. Today, I'll present the findings of my physics laboratory experiment, investigation of coupled oscillations and normal modes. The primary objective of this experiment was to observe the phenomenon known as beats in a system with 2 degrees of freedom. Specifically, I aimed to measure the beat frequency experimentally and verify the theoretical model which suggests that this frequency corresponds to the difference between the system's normal modes. To achieve this, I analyzed the energy transfer between a vertical spring mass oscillator and a simple pendulum. For this experiment, I needed a T-bar and clamps, a helical spring, pendulum masses and string, a smartphone camera for video analysis, precision digital scale, and a ruler. Before discussing the results of my experiment, I must address a critical modification I made to the experimental setup compared to my initial proposal. Originally, I planned to conduct this experiment horizontally using a spark table and a cart. However, I encountered significant engineering constraints during the setup. First, the spark table's raised peripheral edges restricted the pendulum's motion, creating collision risks. Second, when I attempted a linear guide setup using rulers, the mechanical friction was excessive. The system became overdamped and stopped before completing even a single full oscillation cycle. To solve this, I transitioned the experiment to a vertical spring mass pendulum configuration. In this vertical setup, the only deceptive force is air resistance, which is much weaker than the mechanical friction. This allowed the system to sustain oscillations long enough for accurate data collection. Theoretically, this system operates under the weak coupling approximation. This means we can model the motion as the superposition of two independent normal modes. Spring mode, determined by the spring constant and total mass. The pendulum mode, determined by gravity G and length L. Using my parameters, a spring constant of 5 newtons per meter and a pendulum length of 21 centimeters, I calculated the theoretical nature of frequencies. The pendulum frequency, Fp, was found to be 1.087 Hz and the spring frequency, Fs, was 1.221 Hz. Therefore, the executed theoretical beat frequency, which is the absolute difference between these two, was calculated 0.134 Hz. To test this theory, I recorded the motion in slow motion to capture the high frequency oscillations accurately. I used the tracker video analysis software to extract data. By tracking the center of mass of the wooden block, I generated the vertical position versus time graph as you can see on the screen. This graph serves as the most critical evidence of our experiment. You can clearly see the envelope pattern. The high frequency oscillations represent the carrier frequency. The periodic rise and fall of the amplitude represents the beat frequency. Specifically, notice the nodes where the amplitude drops to nearly zero. These are the moments when the energy has almost completely transferred from the vertical mass to the pendulum. From this graph, I measured the time between successive stops, the beat period, as 8 seconds in real time. This corresponds to an experimental beat frequency of 0.125 Hz. Comparing this to our theoretical value of 0.134 Hz, we obtained a percentage error of only 6.7%. This small discrepancy is primarily due to two factors. First one is air resistance, which causes the gradual decay in the amplitude as you can see in the graph. Second, spring mass. Our simplified theory assumed a massless spring, but in reality, the spring's mass slightly affects the frequency. In conclusion, despite the initial mechanical challenges, the vertical setup successfully demonstrated the coupled oscillations. The experimental data validated the weak coupling approximation with high accuracy. For future iterations of this experiment at Bilkent University, to further reduce the error caused by air drag, I recommend using a denser, heavier primary mass to increase the inertia. Alternatively, Using a functional air track will be the ideal solution to observe the horizontal motion without friction. Thank you for listening.